Okay. Hello, everybody. Good afternoon. Today we're going to finish up enzymes. Today is going to be a pretty hardcore session, relatively. It's not going to be, uh, all questions, and it's not going to be all content, but we're going to do a little bit of what we can in terms of practice questions. I looked back, and there's a little bit more content than I thought we'd have to cover. And I got a lot of people asking questions specifically about the slides I'm about to cover. So I'm going to spend a little bit more time than I anticipated on those, but I do have a good amount of practice questions in the slideshow, and we're gonna go as far as we can, and whatever we don't get to, we will. You'll have it available to you on your Canvas. I'll post the slides, and it'll have the question and then the answers on the next slide, so you can go through those at your own leisure. I will not be reviewing anything involving proteins, hemoglobin, or enzymes 1, which I believe is slides 1 through 32, just for the sake of time. I'll be covering enzyme kinetics and on, so what we talked about last time on Friday. If you do have questions, though, on other things or something that was mentioned before the enzyme kinetic portion, please feel free to reach out. Just because I can't do it on this session, just because we are limited for time, doesn't mean that you can't ask the questions. So if you have questions on proteins or hemoglobin or anything before protein kinetics, email, WhatsApp, preferably reach out to David. He couldn't make it today, unfortunately, but he did cover those topics, and I don't want to like kind of step on any toes here because he taught you in a certain way, and I don't want to confuse anybody. But if he can't get back to you, I'm more than happy to help as well. And if you have any questions, of course, regarding enzyme kinetics on, everything that we talked about on Friday up to everything we talk about today, and you have questions, I will ask you that you please hold your questions till we get through the lecture, because it's more than likely that your question will answer itself as we proceed through, right? Especially with the practice questions, and a lot of the new material will tie into the older material. So just for the sake of time, because I don't want to have to reiterate more than I have to, especially for those watching at home, watching the recording, they don't want to hear me talk more than I have to, and I don't blame them. So if you do have questions, write them down, put them on the side, and if by the end of the session they aren't answered, just copy and paste that right into my inbox, and I will have you an excellent answer, as good as I can give before the end of the day. And are there any questions? Are there any questions before we get started? Are you guys excited? I'm excited. All right. All right. So moving forward, just think of your TAs. So this is going to see how good you guys know your stuff. Think of your TAs as the enzyme, right? Think of you as the substrate, and a refined biochem powerhouse of a student as the product. And you might get there eventually, but we're here as enzymes, TAs, to help you get there faster, right? And that makes sense. So let's bump up that activation energy, pop on your biochem shoes and your thinking caps, and let's get started. All right. I'm gonna first of all, that was corny, huh? Yeah, you guys, I'm getting cornier and cornier. It's getting crazy. All right. Yeah, it gets better, guys. Just wait till we get to semester 2. Thanks, AM. All right, let me go ahead and just share my screen. I have to transfer hosts, I think. Multiple participants can share. Yes. Okay. How do we do this? Share content. Share my screen. Yes. All right. Everyone see my screen? Yes. Good. Okay, let's get to where we were. We talked about all this. We talked about all this. Let me turn off my camera. Get rid of admit. Oh man, we got a lot of people coming in. We're breaking records out here, people. Okay. All right. Where did we leave off? We left off. Enzymes continued. Okay. Okay. So we talked about a lot of important things, and now it is time. We talked about the basics, and now it's time to jump into the meat and potatoes, what you've all been asking for. Oh, yeah. Inhibitors. I hope you guys are pumped because this is going to get a little bit intensive. Try to follow along as best as you can. You're not going to get it on the first time. I can assure you that. Definitely do the best you can to try to pick up what you can where you can, and then as you rewatch and as you go through your lectures and different practice problems, things will certainly get clearer and clearer as you go. As I said, this is the topic where you really gotta hit the practice question, just hit the notes over and over again, and just familiarize yourself with that active recall strategy that we talked about in the first session. All right, so oh wow, we got a lot of people coming in. I love it. Yes. Okay. Don't worry, it's not as bad as it sounds. And at first, yeah, you know, when you don't know and understand the basics of your Michaelis-Menten kinetics or your Lineweaver-Burke plots that we talked about, but at this point in time, you should be very familiar. You've seen these things enough times to at least have an idea of what we're looking at, because what we're going to get into is very largely based on that Michaelis-Menten kinetics and those Lineweaver-Burke plots. And they're going to give you a lot of information that you're going to need on test day. Right. So the reason we're so interested in this topic, again, because, I like to look at things in terms of practicality. It's because of pharmacological implications of inhibitors, right? Inhibitors are all kinds are used to interfere with certain parts of physiological pathways, especially and primarily in the treatment of disease, right? So like aspirin, that's going to be an irreversible inhibitor. Well, and you're definitely going to learn a lot about that as you go on, and then as we talk about the COX pathway, the cyclooxygenase mediated arachidonic acid metabolism. And yes, you will know exactly what I just said in a few short months, believe me, and you're going to feel super smart for it, I promise. Nexium, esomeprazole, that's right. That's a medication used for GERD and heartburn. That's an example of a proton pump inhibitor. And the proton pump, as we all know, it's an enzyme. So in doing so, if we inhibit that proton pump, we're going to lower the amount of acid in someone's stomach that's causing all those problems and all that. So these are important. This is gonna if you're pre-med in any way, shape, or form, this is going to not just come up, it's going to form the foundation of your treatment of the patient. So definitely pay attention, do yourself a favor. If you're not muted right now, I will ask that you go ahead and mute. And again, if you have questions, just type them on out. If it's a small, quick question, yeah, of course, just shout it out. I'm happy to answer. But if it's a question that will require, you think, a little bit of explanation, just keep it on the side. And as we go forward, ideally, it will answer itself. Because I'm going to go through a lot of the old and new stuff conglomerated together. Hello. Listen to the question. All right. Go ahead and mute if you're not muted right now. How do I do this? How do I do this? Hey, Jade.
Hello.
Hi, can you go ahead and mute for me?
Oh, sorry. I thought I was muted.
No problem.
Wait, am I logged in two places? Because I'm muted on this one, but I'm not muted on the other. Let me leave and come back. Oh, sorry.
No problem. Sorry, I didn't mean to call anyone out just now, but gotta do what you gotta do, All right. Okay. Yeah, let's jump on in. So remember when we talked about affinity, right? What did we say was a good indication of affinity before we get into the enzyme portion? We said, am I? All right. We said that affinity, right, could be determined or can be isolated by looking at the Km, right? That's how attracted one thing is to another. That's the definition of affinity. And we know that the lower the affinity, the higher the Km, and the higher the affinity, the lower the Km, right? So for an inhibitory drug to be considered quote unquote good, right? Quote unquote good, to be considered effective in a pharmacological, medical, clinical setting, we got to look for one with a lower Km. A lower Km at least than the original ligand or substrate that will be binding. And that means when added to a solution, the inhibitor will be more likely to bind with the enzyme than the substrate would, thus leaving less room for the functional enzyme substrate complex to form, right? And which in turn means less product formation, right? That's the point of an inhibitor. Does that make sense? Good. So yes, excellent. Thank you. Yeah, just go ahead and use the chat. You know, I'm gonna ask a few questions here and there. And yeah, just write in the chat, just go ahead. Thank you, Shireen. So for an inhibitory drug to be considered good, we want a little bit of a lower Km, right? Because that's gonna make it hit a little bit harder. It'll make it do its job better. It'll allow for less product formation. So the bottom line here, and as indicated, right on over here, is that enzyme inhibitors function to interfere with catalysis. So they're going to slow or halt your enzymatic reactions. That's the whole point. That's what we're trying to do here. We want to take what would originally have been an enzymatic reaction and either slow it down or entirely stop it for the purposes of achieving whatever goal we're trying to achieve. Okay. So we have in the inhibitor category both reversible and irreversible inhibitors. We're going to go first through the different reversible inhibitors, and then we're going to go through the irreversible. Okay, so the term in reversible is exactly what it sounds like. The effects of inhibition are transient. In other words, they're not permanent. They're not locked in there for good. They can attach and then detach, attach and detach. And the thing within reversible inhibitors is that there's multiple kinds, right? 4 to be exact, and those are listed over here. Competitive, uncompetitive, mixed, and non-competitive. Those are your reversible inhibitors, right? So before we move forward, I'm going to implore you guys to think of these things in maybe kind of like a flow chart type of modality, right? So let's say this is what helped me a lot when I was studying, just to help isolate what was what. So you have your reversible, right? So we'll put inhibitors up here. And that will break up into either reversible or irreversible, right? And now we're focused on reversible. So we know the reversible are going to break up into 4 different kinds. You're going to have competitive, uncompetitive, mixed, and non-competitive, right? And then these will break up and break up and break up further. Irreversible, we'll talk about, are going to break up and break up and break up further. This will help you keep track of what we're looking at. And that's important because, you know, you need to see where everything fits into the grand scheme, the big picture. That's what's really going to help you understand what we're talking about. Because Dr. Peterson is not going to ask you, what is the definition of a competitive inhibitor? No, that's not going to happen. That's too easy. That's high school stuff. Right now we're in medical school level material to the point where she's going to give you a set of scenarios. She's going to give you a set of conditions, right? Blank exists in 45 degrees Celsius with a substrate concentration of this. This is the curve. Explain to me, insert whatever property about the curve. And you have to be able to take all the different aspects that you learned in these lectures, think of them collectively and spit out an answer. You're not going to get simple definitions like that. So really do become familiar with what we're looking at over here. All right, so let's just jump into specifically what we're talking about. At least the basic aspects of the different types of reversible inhibition. So I'm just going to read quickly off this slide because it tells you everything you got to know. Competitive inhibition, the first one we're going to cover. The inhibitor is going to bind right at the active site, right at the active site. So let's say that here is the enzyme. Here is the substrate, right? Normally the substrate would go right on into the enzyme, right? But no, in the case of an inhibitor, here is the big bad inhibitor, right? It has the same shape. It looks and disguises itself kind of to be the same thing as the original substrate, but the inhibitor will usually have a higher affinity, right? A lower Km, a higher affinity for this enzyme, and therefore it's going to swoop on in there and occupy this active site. So now this poor dude over here, he can't get in there. And that is basic. That's the basic idea of competitive inhibition. Now it's going to get, again, a little bit basic in the beginning, but I promise you it'll speed up as we go. I'm trying to really lock in the basics before we step into the harder material. So yeah, there's your competitive inhibitor right at the active site, right at the active site. Uncompetitive inhibition. Here, the inhibitor binds only to the enzyme substrate complex and not to the enzyme. So in competitive, we're binding to the enzyme. This is our enzyme. In uncompetitive, we have the enzyme here. Substrate that was over here. The substrate is going to come in and it's going to bind. Now we have the enzyme substrate complex, right? We have the enzyme substrate complex as it should be. At this point, our inhibitor then is going to come in and bind over here to the whole enzyme substrate complex, rendering it useless, right? Rendering it useless. You cannot produce product, right? We judge the value of an enzyme by its ability to form a product, or their value of a reaction, rather. And if you have this inhibitor coming on in here, binding to the enzyme substrate complex, now you have less working substrate and you have less working enzyme. What does that mean? You have much less product, right? Much less product. I'll try to clean this all up for you guys. It'll look nicer when I post the slides, but I'm just trying to talk you through it for the time being. Okay, now this is a very hypothetical scenario. Uncompetitive inhibition. This doesn't really happen in real life. Okay, we haven't actually documented an enzyme to that does this, but it's going to be on your MCAT if you're taking the MCAT or your DATS or anything similar proficiency exams. Medical school will mention it, and as you all know, this is a pre-medical focused biochemistry course, which is why we do get so deep into the weeds and into pathologies and whatnot. So you're not going to really see that in real life, but it gives you a nice little contrast to competitive inhibition. Now, that is not to be confused with non-competitive inhibition, right? Because so this un and this non can get a little bit confusing for some people, and I know it was for me. I try to think of mnemonics, and but I just ended up memorizing it, guys. And you know what? That's gonna be what it comes down to at the end of the day for a lot of these things. It's gonna be a matter of, okay, can you memorize this or not? Like I wish there were easier ways of going through things like our amino acids. At least you have, some mnemonics you can use. There's a few good ones out there. I'll try to post those as well, even though, I didn't really cover those, but I had a pretty decent system to memorize those. I'll send them your way. But yeah, a lot of this just does come down to memorization. Become familiar with the difference between uncompetitive and non-competitive, because non-competitive inhibition is when the inhibitor can bind to either the enzyme or to the enzyme substrate complex. So theoretically, don't write this on your test, but the way I thought of it was a non-competitive inhibitor is under the umbrella, or actually Dr. Peterson did mention this, under the umbrella of mixed inhibition, right? So think of this as a little bit of a sub piece of mixed inhibition. Mixed inhibition is when the dissociation constants of the inhibitor to enzyme and the inhibitor to enzyme substrate complex are different. That's a bit of a complicated way of saying it. I understand that. Bottom line, the inhibition is mixed. We're gonna go into the details of each one of these 1, 2, 3, 4 individually, and I hope by then that'll help clear things up a little bit. But for now, you have the general idea, right? So let's just move right on in to our competitive inhibitors. I know when I got competitive inhibitors on the exam, I was hyped because those are usually the more straightforward examples. But like we said, where does that competitive inhibitor bind? Let's see who's paying attention. Someone put it in the chat. Where does it bind? Right to the enzyme. Thank you, Tanishka. Yes. Right to the enzyme, to the active site specifically of the enzyme alone. Now, we'll talk also about what are called allosteric inhibitors, and those do not bind to the active site. They bind to an allosteric site, a separate site from the active site, even though they may bind indeed right to the enzyme. Definitely specify and say the competitive inhibitor will bind to the active site of the enzyme alone and not the enzyme substrate complex, because that's something different, right? We talked about that. That's uncompetitive inhibition. Don't they also cause a conformational change? That's actually a great question. Yes, a lot of people do believe that in doing so, it'll create a conformational change. That has to do with what's called the induced fit theory. I believe David covered that as well. But yeah, for the purposes of this portion of the lecture, you know, don't think too much about conformational changes. We will get into it a little bit as we move forward. But yes, I am. It can absolutely. Okay, so here is our lovely Michaelis-Menten equation. And I know that we spent our whole weekend getting super intimately familiar with this equation. I'm just kidding. I know there are better and funner ways to spend our weekends, but we are here today, and that's the important part. And today we're gonna really look into this equation, the Michaelis-Menten equation, because after all, the enzyme kinetics that we're looking at, that we're discussing right now, are Michaelis-Menten kinetics. And even the Lineweaver-Burke plot is simply derivative of the Michaelis-Menten curve, right? The Michaelis-Menten equation turns into the Lineweaver-Burke equation. The Lineweaver-Burke equation becomes the Lineweaver-Burke plot, right? The graphs are nothing but a graphical representation of the equation. So sometimes you might get enough information to only answer with the equation. Sometimes you might get enough information to only answer with the graph. You have to be able to use both, okay? Now, in the presence of a competitive inhibitor, emphasis on competitive inhibitor, the Michaelis-Menten equation becomes this right here, okay? Now, I don't want you guys to get too confused, you know, too bogged down with these details here. Yes, they are important. Yes, you should know them. And yes, they might be actually what differentiates the person who gets a 100 on the test from the person who gets a 93 on the test. Okay, I'm not going to tell you that this information is not important, but for now, while we're getting the basics, I think it might be more useful to just focus on this portion here. Okay, if you're feeling really good and you've put your work in, then yeah, come back here and look into these aspects. Okay, because this really helps make things a lot more complex than I think we should go into today. But over here is where I want you to focus right now. Let's look over here. So what's different between this one and this one? The alpha. Aloha. Aloha to you too, Aisha. The alpha, yes. Okay, so this alpha is going to represent something called the apparent Km, right? So this is not the actual Km because the Km really is only, it's restricted to the enzyme and the substrate, and that's it. The apparent Km is what we talk about when we have an inhibitor. And that's how we're going to denote it, alpha Km. Okay. Again, don't get too bogged down in those details. Just know that the apparent Km is what we're going to see in the presence of an inhibitor. Yeah. I will mention this constant here, Ki. Ki stands for the inhibition constant. This is going to be pretty huge in pharm. Okay. And we will definitely get into that in a few slides, a little bit more. But, keep in mind that Ki equals inhibition constant. Alpha is apparent Km. Can anyone remind me what the Km means? What's the Km? This is a 1/2 V max. Tanishka's on a roll. Yes. Yes. Oh, you know what? Let's just, yeah. So Ki is right here. So we'll talk right about it. Okay. What is Ki? This is going to indicate, it's going to basically tell you how potent, or in very broad terms, how effective is this inhibitor, right? So this is the concentration of inhibitors that we need to produce half maximal inhibition. So that, that sounds kind of familiar, right? So in practical terms, if we have an inhibitor where a very small concentration can yield a big response, something like I'm not going to give a specific example. I was going to say fentanyl. All right, fentanyl, you need a very small amount to yield a huge response, right? But I wouldn't classify that as an inhibitor. But the principle stands, right? Potency. Ki, think potency. Think how hard is this inhibitor going to hit? Yeah. So we're looking at a very potent inhibitor. If we see, if we see that a small amount can yield a large response. Okay. And I want you guys to look at this table and try to tell me, will a lower Ki or a higher Ki indicate a stronger inhibitor, a more potent inhibitor?
Lower.
Yeah, the lower the Ki, the stronger the inhibitor. Absolutely right. Yes. So if you have a lower Ki, take a look at these here. You guys should look at this chart, and it'll show you the trend you need to know. But yeah, bottom line here, lower Ki equals more potent. Okay, that's what I need you to take from this slide. Let's move forward. This is a pretty straightforward slide. It's competitive inhibition. We talked about this. This is what I showed you guys. The inhibitor competes with the substrate for the active site of the enzyme. Right. So here's your enzyme. It can go one of two ways. It can go one, or let's do this. We can go 1 or 2 in the presence of an inhibitor. Now, just because you put an inhibitor in there doesn't mean, oh, now suddenly it's all going to go this route 2. No, because the inhibitor will take up certain parts and the substrate will take up other parts, but as you add more inhibitor, we're going to see more going this way. As you add more inhibitor, we're going to see more enzyme inhibitor complexes forming, and less product forming as a result, right? If I add more substrate in the presence of an inhibitor, right, we're going to go this way a little bit more. Okay, we're going to get into that in a few slides as well, but just try to think of the semantics behind what I just said. Okay, there are a couple of ways it can go. So pay attention to these slides here as well to follow, because now we're getting into the really testable portions of inhibition. So, title. Titles are important. Titles say a lot. This tells you what you need to know about competitive inhibitors in terms of the apparent KM and the Vmax, right? So competitive inhibitors will affect the apparent KM, but will not affect the Vmax. It will not affect the Vmax. Now, the reasoning behind this is that enough, like I just said in the last slide, enough substrate relative to inhibitor is often enough to overcome the inhibitor. So if I have a little bit of if I add a little bit of inhibitor, right, and then you see, okay, the Vmax dropped a little bit, and then I pour in a whole bunch of substrate, then the Vmax is going to come back to just about normal, because there's going to be a lot more. If we flood the system with inhibitor or with substrate, there's obviously going to be more substrate to enzyme interactions, and it'll be able to form those enzyme substrate complexes, you know, much more than if there was just a little bit of substrate. Does that make sense? No, it doesn't. Okay, so let me put it in a different way. And I'm glad, yes, please, yeah, let me know when these things happen, because it is a little bit hard to really verbalize these things. And as you guys notice, it's gonna become a lot of looking at these things on your own. But let me just go ahead and try to reword that. Okay, so let me try to draw some pictures here. How do I look at this? Okay, so competitive inhibitors are not necessarily going to affect the Vmax. Let's focus on the not the Vmax part, right? The Vmax is talking about the highest level of product we can form, right? The highest rate of product formation that we can form. So if I have little I and little s in a big tub, right? At this point, the inhibitor will and the substrate are in relatively equal levels, right? They're pretty much equal, right? And at that point, we will see a drop in Vmax. Does that and that makes sense? Here's the enzyme. Normally, we'd have the substrate come in, and then that would give us a product. But in the case of inhibitors, if we have an inhibitor come in, we block that active site, and now the substrate cannot come in. And if the substrate cannot come in because the inhibitor is taking the place of where it should be, we are not going to get product, right? So since we're getting no product, we're getting less product, right? Less product means what? A lower Vmax. Does that part make sense? Just that part. Yes, okay. So you understand now why an inhibitor is going to lower the Vmax of a reaction. Now, let's say these two are not equal anymore, right? I have the same amount of inhibitor, but I put a ton more substrate. A ton more substrate. I have a lot of substrate in here, right? So much substrate now that it can overcome this inhibitor. If I have a lot of substrate, what does that mean? More enzyme substrate complexes, more product can be formed. If I have a little bit of substrate and a lot of inhibitor, I'm going to have much fewer enzyme substrate complexes, right? If I have a lot of inhibitor, I have fewer enzyme substrate complexes and less product. Okay, so all that I'm trying to say here is that if you have a whole lot of substrate, if you have lots of substrate, you can overcome the amount of inhibitor in there as long as you have enough. Okay, so if I pour in a bucket load of substrate on top of a small amount of inhibitor, you won't really have to necessarily affect the Vmax. Does that make sense? Yes. Does that not make sense to anybody? Because I'm happy to this is important. We do have to get these basics down. Okay, good. Yeah, and that's really the idea that I'm trying to get across with this whole slide here. Okay. The bottom line when it comes to competitive inhibitors is you're going to see a change in Km and no change in Vmax. So will you always have more substrate with a competitive inhibitor? No, not necessarily, right? Because let's say I start here. Substrate concentration is 1. Oh gosh, I'm in a laser, my bad. Substrate concentration is 1. We're not going to include units just for simplicity's sake, right? And inhibitor concentration is also 1. Now you're asking, will you always have more substrate with a competitive inhibitor? No, it depends how much inhibitor you put in, right? You'll always start with the same ingredients, but the way that we change, the whole point of a competitive inhibitor is we're adding it into the system. We're adding it into the system so that we can lower the product. That's the point of a competitive inhibitor. We want to lower the amount of product being formed. So, you know, if you do add more inhibitor, then you're going to have a lower Vmax. If you add more substrate, you can bring the Vmax back up. Does that make sense? Got it. Awesome. Excellent. Okay, good, guys. This is great. Yeah, definitely stop me and let me know if something is a little bit confusing. Okay, because I'll tell you what, I even had to review these slides a couple of times and reacclimate because this is not easy stuff. You know, but you know, it does make sense once you look over it enough times, a few times. But definitely, yeah, please pause me if you need to and just tell me, hey, wait, can you repeat that part? Okay. All right, let's move on to this part. Lineweaver-Burke plot reveals competitive inhibition. Now the trend in these lines is going to matter. The being able to recognize the different trends with regard to competitive versus maybe uncompetitive, non-competitive, mixed inhibition, that's important. And that will definitely be on your exam. Okay. So, and remember, Lineweaver-Burke plot is nothing but a reflection of the Lineweaver-Burke equation. The Lineweaver-Burke equation is a double reciprocal of the Michaelis-Menten equation. So they all kind of work together. Go ahead and review those earlier slides that we discussed, and you'll see, you know, there's an interconnection for all of this. This is just a linear way. This is just a linear way of representing these lines. Clear? Good. All right, so this is where those key landmarks I told you about come into play. Remember how we said the y-intercept is indicative of 1 over Vmax? And how the x-intercept, here's the y-intercept, over here, that's your 1 over Vmax, right? And the x-intercept is going to be negative 1 over Km. So these are very important. And these are going to help you on the exam. We're going to use that knowledge that this is this value and that these are this value to help us solve a lot of math-related problems and a lot of not math-related problems, more conceptual problems. So let's see what we're looking at using these 2 points. Let's start with the y-intercept. If we look, we're going to see that the 3 lines here, right? These 3 lines are all intersecting at the same point. And we have to recognize as well, this one, as indicated by the arrow here, is the one with no inhibitor. Okay, so these these do have inhibitor. Where are we going? There we go. These do have inhibitor. And we're going to see what the different slopes of these lines mean. Okay. So what does this tell us, this intersection point here? What does this intersection point tell us? It tells us that they're all at the exact same y-intercept. They are at the same value in terms of y-intercept. Now remind me, what did we say is the y-intercept on these Lineweaver-Burke plots? Thank you, Tanishka. Yes, 1 over V max. So if these values are intersecting at the exact same point on the y-axis, that intuitively tells us that the 1 over V max values are exactly the same as well, right? For all three scenarios, or all three lines have the same 1 over V max value. And thus, logic would dictate, right? So if 1 over V max is the same for all three lines, then V max alone must be the same for all three lines, right? Because here, 1 over V max equals 1 over V max equals 1 over V max, right? Just cancel. In other words, V max equals V max equals V max. Here, this is for 1, 2, and 3. 1, 2, and 3. They have the same V max. And that kind of makes sense, right? Competitive inhibitors affect the apparent Km, but not the Vmax, not the Vmax. So the Vmax is unchanged. Vmax, unchanged, the same thing. And that's important. So if you see on an exam, these three lines are intersecting on the y-axis, what does that tell you? Oh, the Vmax didn't change. The Vmax didn't change. So you can write that down on the side. Vmax unchanged. Same thing. Okay, good. So what's the other piece of information we need to determine what kind of inhibitor we're working with? Km. Absolutely right. So the x-intercept line here, these are all different, right? This is where the line crosses the x-axis, which is over here. These are all different. So if this is the original, sorry. If this is the original, right? This is the original uninhibited x-intercept. These are the two inhibitors. We see that they are different. There's a difference in the -1 over Km value. And that makes sense. Why? Apparent Km is going to be affected in competitive inhibition. Does that part make sense before I move forward? Yes, good. So without even analyzing what these numbers suggest, right? Forget about what the numbers are. I mean, granted, we don't even have a scale anyway. We don't know what these specific numbers are. I don't know what these values exactly are. But without even that, I don't even need that. I don't need that. Why? Because I know that these are different because we have different points of x-interception. And what does that tell me? There's been a change. The inhibitor invoked a change in the Km. So Km, or in this case, because there's an inhibitor involved, alpha Km, apparent Km, is not the same. It is not the same. Does that make sense, that part? So that just because here, change. These are changed before we get into the actual numbers. Vmax did not change. Alpha Km, apparent Km did change. And just from that information, we can tell this is a competitive inhibitor. It seems a bit much at first, I know, but it really becomes a matter of, okay, did Vmax change? Did Km change? Depending on the answer to those two questions, you can usually answer what kind of inhibitor you're looking at. All right. Are there any questions? It's okay if there are, guys. Okay, good. Let's move on. Uncompetitive inhibitors. Notice the here. We're talking uncompetitive inhibitors, as opposed to the other alternative, which I will not say right now, but we don't want to confuse anyone. But Dr. Peterson mentioned in class that since uncompetitive inhibitors are binding where? To the enzyme substrate complex, right? Which we would see over here. That's the enzyme substrate complex. Yeah. Enzyme, substrate, they come together. Enzyme, substrate complex. That is where the inhibitor comes into play. That is where the inhibitor comes into play and will bind over here. Now, AM, as you were saying before, which was a very astute observation, and as Dr. Peterson also mentioned in class, I believe, since the uncompetitive inhibitors are binding to the enzyme substrate complex and not just the enzyme directly, we are likely seeing a little bit of a conformational shift here as a result of the induced fit model, right? In other words, once the original uninhibited substrate comes in and binds to this enzyme, the enzyme is kind of going to change shape a little bit, right? That's what the induced fit model is kind of talking about, as opposed to the more lock and key version of things. So when the uninhibited substrate binds to the enzyme substrate, to the enzyme, and gives us the enzyme substrate complex, it's going to kind of change the enzyme a little bit. The enzyme is going to change a little bit of shape, right? And in doing so, what this shape change is going to make room for our inhibitor to come in. That's not a huge thing. She kind of mentioned that, right, on the side as like a side note, but just to tie into what you were saying, AM, yes, that's kind of what happens, right? When, especially in uncompetitive inhibition, we do see a little bit of a conformational change, or at least that's the theory according to the induced fit model. I just thought that was interesting to throw in there as well. Let's move on. So, like we saw in competitive inhibition, right? We start with the initial Michaelis-Menten equation. That's what we're used to, right? We know this already. This is locked in there. Now, as opposed to where we added the alpha to here, instead, we're going to put it over here, and we're going to call it alpha prime. Okay? There's an alpha prime value here, and this time it's going to be in front of the substrate concentration in the denominator. And it really is just easier to commit these differences to memory, guys, than to try to work out the reasoning every time on a test. Like, you can go through exactly why and work out the math and the explanation, but just know that, at least this is what I would do, maybe because I'm not the best mathematician, but uncompetitive inhibition, you put the alpha prime over here. Okay, just in case the equation itself does pop up in the exam, it's good to know. All right, this is the more mathematical aspect of things. Let's look at the graphs. Okay. Now, contrary to our competitive inhibitors, in uncompetitive inhibitors, we're going to see both the Vmax and the apparent Km change. They're both going to change. So let's just run through this here. The measured Vmax decreases because at high substrate concentrations, the initial velocity approaches Vmax over alpha prime. Confusing, right? This might help. The enzyme substrate complex is prevented by the inhibitor from releasing products, right? It's easier when you look at it in terms of practicality. These equations kind of confuse me a little bit. If you can get them, Godspeed. Like that's I applaud you because I'm not the best mathematician, but the reasoning in my brain that V max is changing, the reason that V max decreases is because the enzyme substrate complex is prevented by the inhibitor from releasing products. Remember, in uncompetitive inhibition, the inhibitor is going to come in after the substrate already is binded, right? So this is your enzyme substrate complex, ES complex. Once that's formed, then your inhibitor comes in. So not only do you lock in the enzyme and prevent it from working, you also kind of locked in some substrate as well, right? You've rendered both of these useless in the system by adding the inhibitor. So if you have less substrate, if you have less enzyme too, what does that mean? You're going to have less product. You're going to have less product. Less product means what? Lower V max. I'm so sorry for the handwriting, guys. I understand it's kind of all over the place, but if you're, just follow along with me because I'm trying to illustrate a few points. I'll clean this up a little bit for the actual slides, I promise. But does that make sense? Uncompetitive inhibitors bind to the enzyme substrate complex, rendering both the enzyme and the substrate pretty useless. Pretty useless. And if they're both not useless, if they're not doing their job, we're making less product, and that's why the Vmax is going to drop here. Vmax is going to drop. Vmax is going to go down. Okay. So here we're looking at probably the uninhibited line. This is the normal untouched line, right? No one threw in any inhibitor yet. Now you put in some inhibitor. You bring some inhibitor in. And look at that Vmax. Look at that Vmax. Totally different. Much lower. Right? And as a result of that Vmax being lower, we know what's going to change. Our Km is going to change because Km is what? 1/2 of Vmax. 1/2 of Vmax. So let's take a little look here, right? So I'd say Vmax is somewhere around 0.5, right? Okay, so we're going to look for the value at 0.25, which I'd say is somewhere around here. Okay. Yeah, somewhere around here. If we look at that, we've got the Km over here. Okay. As opposed to this Km, right? This Km with the uninhibited, this is 1/2 of their Vmax. It'll be more over here. And we're gonna look more at some different graphs, but you get the idea. Apparent Km decreases. Now, usually we'd think, hey, that's kind of a good thing. I'm sorry. All right, AM, sorry. So as far as the Michaelis-Menten equation goes for the inhibitors, does it have to do with the placement of the alpha prime? Yeah, pretty much. For the competitive, we're looking at it. The alpha, alpha is going to be in front of the Km, and alpha prime is going to be in front of the denominator substrate concentration. Okay, so they're two different things. Alpha is going to be apparent Km. Alpha Km is apparent Km. Alpha prime substrate is going to be your apparent or your inhibited substrate formation. Again, don't pay a huge amount of attention to the alphas and the primes. I mean, I personally don't remember actually learning that during my time in biochem. Granted, this is a little bit of a different type of course, but I didn't learn it that way, but I can't imagine it's going to be a huge aspect of the exam. I think she really wants you more to focus on the trends and how to distinguish between competitive, uncompetitive, non-competitive. If the equations do help you, then yeah. So Alpha prime would only be applicable in this situation. In uncompetitive inhibitors, you wouldn't see that. You wouldn't see that in competitive inhibitors like you would. Where was it? Come on. Where is in competitive inhibitors? Over here. You'd only see the alpha up here in front of the KM in competitive inhibition. Makes sense. Thank you. I wanted to make sure I'm picking up the correct patterns. Very good, AM. I'm glad that you're looking at these things and thinking into it. Absolutely. But yeah, guys, you know, don't start off without getting too bogged down in the details. Absolutely. And then, you know, if you're like KM and you've got the conceptual part and you want to break down further into more of the arithmetic aspects and the alphas and alpha primes, then then it's time to look at those things, you know, but you got to make sure you get the general ideas first. Okay. So quick review of uncompetitive before we move on. Once this inhibitor is bound to the enzyme substrate complex, let me get rid of all this stuff. I'm not a technology guy, but this Notability app is pretty darn cool, man. I'll tell you the truth. All right. Enzyme. Substrate. Enzyme substrate complex. Once the inhibitor comes in and binds to the enzyme substrate complex, the enzyme substrate complex is stuck. It's useless. And even though, yeah, it's reversible, this is a reversible inhibitor, there will still be a very visible effect in both your apparent KM and your Vmax. Okay, so if we add more inhibitor, we'll see lower and lower Vmax values, which we do see happening here on the curve, right? Here we have the most inhibitor. Here we have some inhibitor. And here we have no inhibitor. Does that make sense? As we get more inhibitor, the Vmax gets lower and lower. More inhibitor, less product. More inhibitor, less product. Does that make sense? Beautiful. Okay, let's move forward. Let's look at the Lineweaver-Burke aspect of our uncompetitive inhibition. We saw here, this is the Michaelis-Menten curves, right? Curves. Now we're looking at the Lineweaver-Burke plot. These are also fun when you get them on a test, right? I love when I see these on a test. Why? The lines are parallel. The lines are parallel. I don't have to sit there and break down, oh, this is here and this is here and this is no. If I see this, we're talking uncompetitive. We're talking uncompetitive inhibitors on the Lineweaver-Burke plot, and the lines are parallel. More importantly, there's no intersection. What did we say the intersection at the y-axis means? Well, what is
They all cross over the same, or yeah, one.
You broke up there a little bit. I'm sorry, but yeah, it basically means if they're all intersecting at the same point in the y-axis, they have the same Vmax, right? Because the y-axis the y-intercept is 1 over Vmax, right? Yes, Freda, yes. 1 over Jermaine, absolutely, yes. You guys are killing. Yeah, so these aren't intercepting. These are at different points. So we know now, just from looking at this, we know that Vmax changes. We don't even got to know, do they go up or down? It doesn't make a difference. They're different. They changed. They changed. If these were all intersecting at the same point, then we'd know the Vmax is the same and it would be unchanged. But here they're parallel. They're at different points. Vmax changes. They're not the same. And the same goes for our Km, right? Km, Km, Km. Granted, yes, we're looking at negative alpha prime over Km, but we all know, basic math, these must be different. These must be different. They're not sitting at the same, if they were all on the same exact point, if they were all touching this blue dot here, then the Km would be the same, but they're not. They're all at different parts on the x-axis. They're all at different parts on the x-axis, meaning what? Yes, lovely Km or apparent Km changes as well. And remember, what did we just say about uncompetitive? Uncompetitive inhibitors affect both the apparent Km and the Vmax. Uncompetitive. Uncompetitive. If I see this, I'm more than likely talking uncompetitive. Okay? Get these things, get these rules in your mind. That is key. Okay? Let me move 1 second. Just gonna watch. Okay. Again, don't really worry too terribly much about the equations. You do need to know the Lineweaver-Burke equation. You do need to know the Michaelis-Menten equation. But for now, while you're getting the conceptual aspects of things, if it helps you, you can look at that. But for now, look at these trends. Look at these trends. Look at the y-intercepts. Look at the x-intercepts. That'll tell you what you really need to know. Okay, just for now. And I'm not saying these equations aren't important, because they are, and they do tell you what's happening on the graph. But again, the graph is just a representation of the equation. So again, don't flood your brain with too much stuff. Get the basics down, and these are the basics. Your y-intercept, your x-intercept, right? Parallel or not, these things, once you get these things down, then you can move forward into the more aggressive, mathematical aspect of things, or at least that's my opinion. Some people might say, no, the math is more important. That's totally fine. That's your prerogative. But the way I learned math, or the way I learned enzymes good enough at least to become a TA here, I guess, was taking things one step at a time. Yeah, good. Let's jump on into mixed inhibition. Mixed inhibition. Okay. A mixed inhibitor binds at a site distinct from the substrate active site. Interesting. It binds at a site distinct from the substrate active site. Interesting. Okay, we'll keep that in mind. It binds to either the enzyme or the enzyme substrate complex. What in the world? Okay, I thought we just talked about those two. I thought competitive binds to the enzyme and uncompetitive binds to the enzyme substrate complex. Oh, that's why they call it mixed inhibition. I see. Okay, so it's doing a little bit of everything, and it's getting a bit more complex now. Now we're really jumping into things. Freda, I will get back to you on that, because I'll tell you the truth, I do not know. I'm not sure about the derivation of it, off the top of my head. I'd have to go back and work it out. But if you shoot me a text afterwards, I'd be happy to break it down, more intelligently for you. Yeah, I'm just gonna keep it G with you guys, so okay, mixed inhibitor. Let's move forward into the lovely equation aspects. Okay, at this point, when we're looking at the Michaelis-Menten equation, this can be helpful in terms of the equation. You have an alpha and you have an alpha prime. You have two alphas. So if you're looking at an equation and you see two alphas, you're looking at a mixed inhibitor. If you see alpha and alpha prime, you're looking at a mixed inhibitor. Didn't we say earlier that the inhibitor binds to E? And the enzyme substrate complex. And the KDs are different. I'm sorry, I am. Could you just elaborate? I'm not sure what you're asking. We said so. Let's just run it back right quick to competitive, right? Competitive inhibition. In competitive inhibition, the inhibitor competes with the substrate for the active site of an enzyme. So in competitive, we're going to bind to the enzyme. In uncompetitive, we're going to bind to the enzyme substrate complex only. Competitive, you bind to the enzyme itself without the substrate. Uncompetitive, you bind to the enzyme substrate complex when they're already came together, the enzyme and the substrate. And that's all we really went through so far. I hope that answers your question. If not, just go ahead and type it out and leave it on the side, and I'll definitely get back to you with a more in-depth explanation. Okay.
All right. Yeah, you got to me. Thank you.
Got you? All right, good. Excellent. Okay. So one thing about mixed inhibition is it's kind of cool because it'll also include the next type of inhibition, which is non-competitive, right? We did competitive, we did uncompetitive, now we have mixed. And in that little umbrella, of mixed, oh my goodness, of mixed, here we're going to have under there, we're going to have our uncompetitive. And we'll talk about that next. But for now, I need you guys to just know a mixed inhibitor is going to bind to either, this is the most important part, it'll bind to either one. So you can go either this way, enzyme substrate, right? Enzyme plus substrate gives you the enzyme substrate. And it can give you the product. And the inhibitor can bind either to right to the enzyme substrate complex, or the inhibitor can bind right to the enzyme. Okay. That's what this is all trying to show you. It looks kind of confusing. It's not. It's just saying this is all saying this right here. Okay, let's move forward. So this is where, you know, as if it wasn't getting tricky enough, this is where it does get a little bit. Sorry, let me read these real quick. You know, let me get through the next couple slides, and that might answer the questions, I'm hoping. If not, then maybe I said something incorrect, but we'll definitely clear this up in the next couple slides, guys. Okay. So this is where things do get a little bit tricky. Again, I'm not sure how much explanation is going to be effective here. It is just a matter of taking a look at the different trends and really looking at the graphs over and over again. But let's just read through the slide. Vmax is affected because the effective enzyme concentration on which Vmax depends decreases. Okay. The inhibitor renders some of the enzyme unavailable to create product. That makes sense. Okay, so let me try to put this last bullet into perspective because it's not worded beautifully. Okay, think of these mixed inhibitors as a mix kind of competitive or uncompetitive. Either it'll bind to the enzyme or the enzyme substrate complex. Now, depending on what route the inhibitor prefers based on its affinity, and yes, the inhibitor usually has a greater affinity than the actual substrate does. Depending on what route it'll choose will determine whether the apparent Km increases or decreases. Okay, because we know in competitive inhibition, let's write this down. good color here. In competitive inhibition, there's no change in Vmax. And there is what? There's what happens to the Km? Anyone know? It increases. Yep. It goes up, absolutely. So we have an increase in the Km. Who can tell me what happens in non-competitive inhibition? Or uncompetitive, excuse me. Oh my goodness. I'm mixing myself up over here. Yeah, both go down. Oh, I lost my place over here. One sec. Okay, yeah. Okay. So, like I said, depending on which route the inhibitor prefers. Remember we talked up here about the different routes the inhibitor can take? Let's get rid of all this stuff. It can either go this way, or it can go this way. So one of these ways, when you bind right to the enzyme, right, this would be more representative of competitive, the competitive type of route. If you have the inhibitor over here binding to the enzyme substrate complex, this would be more indicative of the uncompetitive route. So depending on which route this takes, depending on which route has a higher affinity, will determine whether the apparent Km increases or decreases, right? Because we said in competitive, the Km increases. In uncompetitive, the Km decreases. Are you guys following me so far? Yes. Okay. So think of mixed in terms of a mix of competitive and uncompetitive, at least in terms of what route the inhibitor takes. It's going to take one or the other, depending on which route it takes, based on the affinity, we'll know what happens to the Km. So if the inhibitor binds more closely to the active site, we're going to look at more competitive type of traits. And thus, we're going to see an increase in Km. If the affinity is greater for the enzyme substrate complex than it is for the active site, right, then we're going to see a decrease in Km because the inhibitor prefers to take the uncompetitive route, right? Again, it is getting tricky, guys. I'm not going to hold you, man. It's not. It takes a lot of times looking over this. You're going to rewind this video and listen to me talk. I don't know how many times, but that's what you have to do at this point. You know, read it and then read it again. Go to different sources and listen to me talk. Listen to Dr. Peterson talk and look at the practice problems until it clicks, right? And I'm sorry. I wish I had a better way to make these things clear to you guys, but that really is the ticket. That is the trick. You got to keep on practicing, and that's why biochem is so notorious for for being one of the tougher classes, because yeah, it really does all fall onto your lap. Dr. Peterson is an excellent lecturer, probably I'd go as far as to say the best lecturer I've had in New York Medical College so far. No one hold me to that. But she, when she explained it, like I had to look back again and try to really listen a couple of times and understand everything. Okay. So do the best you can and keep reviewing. I'm glad that you guys are sticking with me. I see we got a few people dipping out, and that's fine. I know it can be a little bit overwhelming, but just hang on there. We're getting there. We're gonna get to the questions soon. And if not, then you can watch the recording later, and I hope that that'll help as well. Let's move forward. Lineweaver-Burke, okay? So we talked about the Michaelis-Menten part of it. Here's the Michaelis-Menten part. Let's talk about the Lineweaver-Burke part. Let's just jump right into the meat and potatoes here. Steven, how do I know if it's a mixed inhibitor on a Lineweaver-Burke plot? Oh, okay, I'll tell you. It's the intersection right here. This is this will give it away. No, it's not on the y-intercept, because if it was on the y-intercept, then it would mean what? They all have the same Vmax, which means what? We have a competitive inhibitor. It's not on the y-intercept. It's not, but they are intersecting. They are intersecting, but somewhere over here. Somewhere else. And that is usually a good, strong indication of whether or not you're looking at a mixed inhibitor on a Lineweaver-Burke plot. Does that make sense? How we feeling, guys? How we feeling? It's all right. Just say, Steven, you know, you're scaring me, man. You're scaring me. I'm getting nervous out here, amigo. You gotta you expect a lot of emails, and you know what? That's okay. I'm happy to answer some emails and walk through, because oftentimes with this stuff, it really is just that one little piece of information that you're missing that'll make all the difference. So if I can clear up that one piece, it'll all fall into place, friends. Half and half. Okay. All right. All right. We'll try to bring those numbers up there, Frida, by the end of this session. Now, here's the bad news. And yes, there is more bad news. Even though we do have the intersection and we know that it's probably mixed, you have some work to do. If you see this over here, guys, if you see that intersection over here and it's not on the y-axis, you got some work to do, right? We know it's mixed, which can mean it can and does bind to both the enzyme and the enzyme substrate complex. The annoying part, though, is that we need to figure out which one the inhibitor prefers, right? And as we just said in the last slide, as we talked about, its preference, the inhibitor's affinity toward one or the other, the enzyme or the enzyme substrate complex, that can really have a huge effect on whether the Km goes up or down. And we're going to use that using the same reasoning that we did to explain uncompetitive and non-competitive. Okay, and we'll jump more into this aspect of things and how to distinguish as we get into practice problems, because that really is the best way to do it. Let's try this out. What do you guys think? Oh, sorry, I didn't even slide it up there. My bad. I meant to try this out and then let me know what you guys think. I got two different monitors here going. My fault. A, B. Ooh. Yes, I see what you mean. Sorry. Yeah. Both inhibitors combine to the enzyme substrate complex. Here's the explanation here. I'm not going to run through it. We're gonna try to get through the rest of this. Non-competitive inhibition. Now, I hope this helps answer some of the questions we had before. First of all, before we talk, these are super rare to see. As I said, super rare to see in graduate student settings. They're sometimes on the MCAT though, so Dr. Peterson just introduced it to you guys. Like we said a few slides ago, these non-competitive inhibitors fit under the umbrella of mixed inhibition, but in this case, you know, the alpha will equal alpha prime. Now in mixed, we said we'd see both alpha and alpha prime, but that doesn't necessarily mean that they're equal. In fact, they're not equal unless if they're non-competitive inhibitors, in which case they would be equal. Again, I'm not going to focus on these alphas right now because that's not how I was taught it. That's not how I really, learned it. I don't see it being essential to your understanding of what a non-competitive inhibitor is at the moment. Okay. But, you know, if you really would like to get the absolute, you know, understanding of what's happening, then I'm sure Dr. Peterson could help with that. Or if you email me, I can definitely take my time with it, but we're running a little low on time, so I'm not going to get too into that. Don't want to get too confusing out here. But yeah, that's the main point. It's a special case of mixed inhibition where alpha equals alpha prime, where you have exactly the same amount of Km change and substrate concentration change. This is really not going to show up much, guys. Don't spend too much time on this slide. Don't bang your head against the wall on this. It's the graphs that you have to worry about: competitive, uncompetitive, and occasionally mixed. That's what's going to be on your exam mostly. You know, this might pop up as a special case of mixed inhibition, but don't go crazy over this. All right. Here's an effects of the reversible inhibitors on apparent Vmax and apparent Km. I don't like the way this is worded. I don't like the way this looks. I'd rather you guys did something like here for competitive, we'll just keep it simple. For competitive, I'd rather you write Vmax does not change. Km, apparent Km increases. Do yourselves a favor, fill out this chart according to what we just talked about. Okay, I'm gonna also include the chart that I made at the end of this presentation, and you guys can refer to that as well. But you know, just break it down into simplicity, some simple parts. We don't have to get too crazy about it. Okay. That was all reversible inhibition. That's the really hard part. Okay, we just finished the really hard part, and I'm telling you, the practice questions are going to make them much less hard. The irreversible inhibition part is actually a lot simpler than reversible, in my opinion, at least. Now, these are incredibly powerful. These irreversible inhibitors are incredibly powerful, and there are three ways that they can work. They can either A, bind covalently. They can B, destroy the enzyme's functional group, right? And usually enzymes need that functional group in order to do their job. So here, 1, 2. Or they can form a highly stable non-covalent bond formation. So number 1 was bind covalently, form a highly stable 3 non-covalent association. Okay, moving forward. We're almost there, guys, I promise. Mechanism-based inactivators. You guys can read the slide. I'm not going to go through this too much. It's pretty self-explanatory, but bottom line, the mechanism-based inactivation system is where the product being formed, right? After we form the product, it's not going to work on the next step of the chemical reaction. Okay, so whatever we inactivated, right? Whatever the product is from this whole system, the product, there's something wrong with it. There's something wrong with it, and it cannot continue through steps 2, 3, 4. It's not going to work in step 2. But do read through that. It's pretty intuitive. You'll understand it if you go through. Again, I'm not going to go through this for the sake of time, but do take a look of Dr. Peterson's explanation of these slides, because it actually is pretty interesting. And Dr. Peterson truly is an expert on the stuff being explained in here. So, she can give you an interesting perspective. And this is just basically a good example of how all of the seemingly monotonous things, over here I'm talking about, how all the seemingly monotonous things that we're talking about really do translate directly into the medicine aspect of things. Okay, so go ahead and read that if you're interested. It actually is pretty cool stuff. And let's move right on to the transition state analogs. Another type of irreversible inhibitor. And these have a super high affinity, right? Super high affinity, but they're not going to really give the substrate any chance to go to product. Okay, the bottom line is they're stable molecules, and they're meant to resemble transition states. They're meant to basically be a copycat. Okay, they're irreversible inhibitors. They bind to an enzyme more tightly than the substrate does in the enzyme substrate complex. and they're irreversible. They bind extremely tightly. They have a super high affinity. So when these transition state analogs bind to that enzyme, they're not going to come off in physiological conditions. You know, we can add some heat, we can put some pressure onto the system in a lab, maybe, and then they'll pop off. But in the human body, when you think transition state analog, think permanent. That's it. That's really all you have to know here. I'm not going to do these right now. We have some other questions to go through. What type of inhibitor binds to the active site of an enzyme and undergoes the initial steps of a reaction before combining irreversibly with the enzyme? The answer is B. And the explanation is over here. Feel free to go through that. Okay. I know some people had some questions about this here. So here they were studying Staph aureus. You've heard of MRSA, right? Methicillin-resistant Staphylococcus aureus. This is really just, you know, Dr. Peterson liked to go through the whole discovery aspect of it, which is really, really cool. They found some mold on the Staph aureus, and when they tested it, there was no more Staph aureus around the mold. It was kind of by accident. They figured it out, and then they tried to purify it and to make more out of it. And it was just way too much mold for a tiny bit of medicine. And anyway, the point of things like this penicillin is to work by targeting transpeptidase. This is transpeptidase. And that's an enzyme that we need to synthesize peptidoglycan. Peptidoglycan is just a super important component of the bacterial cell, the bacterial cell wall specifically. And the main idea here is that by using antibiotics, we target that enzyme. We're going to target that enzyme, render it useless. And if we can't use that enzyme, we're not going to make any of the peptidoglycan we need for the bacterial cell wall. The bacterial cell wall will break down and the bacteria will die. The bacteria will lyse, and you know, the less bacteria we have, we're in better shape, right? Long story short, penicillins work by targeting enzymes like transpeptidases, and they help to destroy bacterial colonies from growing. Give it they don't destroy it completely. You know, antibiotics will not destroy the bacteria completely, but they'll bring down the numbers enough for our immune system to mount an immune response and to create whatever antibodies we need to kill it on our own, right? And that's why we want to finish off those antibiotic courses before we just stop them. And yeah, this goes into it a little bit more. I know someone asked specifically about the beta-lactam. This is really just reiterating what we just said. You know, beta-lactam. Actually, that's in the next slide. I'll get into a little bit. What's a second. There we go. So here's the thing. So we use something called an enzyme called beta lactamases, and they are used to cleave beta lactam antibiotics. Okay, so what happened over time as we kept on treating with antibiotics is these bacteria became immune. They became resistant. A beta lactamase is an enzyme that cleaves beta lactam antibiotics. And bacteria that express those beta lactamases became resistant to those beta lactam antibiotics. That's the main thing you have to get here. And compounds that mimic the structure of a beta lactam antibiotic can inactivate the beta lactamases. I feel like this is kind of a mouthful for you guys. Go ahead and read this. I have a little bit of a Star Wars type of analogy, and I will post that into the lecture slides that I post up. But this is not going to be a big part of your test, so I'm not going to spend time on this, guys. Okay, regulatory enzymes. Okay. So the last part of the lecture really just talks about regulatory enzymes, and they're critical because they allow for the cell's state, right? The cell's circumstances to determine what the cell does. For example, if the cell is starving, it'll act in one way. If the cell is fed and thriving, it'll act in another way. So based on what the cell's environment is, right? Are there a lot of food and nutrients available, or is it fighting for its life? Depending on those circumstances, the cell can make changes via these regulatory enzymes to help meet its needs. Pretty straightforward. So how does this regulation happen? It happens in a few ways, and we're going to go through them. An enzyme can have either one or multiple regulatory mechanisms. And, just because we're going to run through them one by one, that doesn't mean that they exist independently. In fact, a cell is better off if they use all of these together or multiple of them together. The more they use, the better they will work. So let's just run it through quickly. Allosteric enzymes. Allosteric enzymes. They function through reversible, non-covalent binding of regulatory compounds called allosteric modulators or allosteric effectors. These are important. They can be either positive or negative modulators. In other words, they can either increase or decrease the activity of the enzyme. So I have certain positive allosteric modulators or positive allosteric effectors. They're both synonymous. That will increase the enzyme's activity. It'll make them work even better. It'll be an enzyme on steroids at that point, right? Or I can have a negative modulator, in which case you're going to have a decreased enzymatic response. Okay, that's your allosteric. And the key to allosteric is that they are going to bind to an allosteric site. And we'll show that in picture form in a little bit, but it's not going to be the active site. You're not going to be binding to the active site. It'll bind somewhere else. Reversible covalent modification is another big one, very big one. So you're going to have covalent bonds forming, like phosphorylation, hydroxylation, ubiquitination, right? The formation of these covalent bonds is going to really change the functionality of the enzyme. One single covalent modification could render an entire enzyme useless or make it even more and like supercharge it, make it really active. It can turn an enzyme on or off. And we're going to see that a lot in metabolism pathways, especially with phosphorylation. That's going to be a big one. We're also going to see the binding of separate regulatory proteins. Right? It's going to be just a different type of regulatory protein will bind on. It's exactly what it sounds like. And then interestingly, we're going to have something called proteolytic cleavage, which if you break down the word proteolytic cleavage, this has to do with breaking peptide bonds. And that often is involved with zymogens. You guys learned about zymogens, right? A little bit. So proteolytic cleavage is bottom line is the removal of peptide segments, like something like chymotrypsin or zymogens like pepsinogen that we talked about, where we have the enzyme in its inactive form, but then we cut off a certain piece of the peptide bond, right? We cut off a certain piece of the zymogen, and now that activates it. That turns pepsinogen into pepsin, or chymotrypsin into trypsin, right? And that'll activate the zymogen precursor, turning it into an active enzyme that can finally go and do its job. And that's proteolytic cleavage. Let's talk about the different types of allosteric modulators. We have two separate types. So allosteric enzymes undergo conformational changes in response to modulator binding. And the two types are homotropic and heterotropic. Homotropic regulation is where the substrate and the modulator are identical. They're the same thing. Okay? In other words, if we fill up all the active sites on an enzyme, let's say this is our enzyme, and it's full. And all the enzymes are in this state. They're all filled on the active site. At this point, when they're all full, there's another site somewhere over here, maybe, where the same substrate, because there's going to be more substrate in the solution, the same substrate can come in and bind in this random other site. This is not the active site. This is the active site over here. This is just the allosteric site. The same substrate, let's say it's substrate A. Substrate A can bind onto here, and the same substrate A can bind onto the allosteric site. And by binding at that allosteric site, we're going to supercharge it. This enzyme is going to go crazy. It's going to really have an increase in enzymatic activity. It's going to become way more active. And that should kind of ring a bell, right? In terms of the homotropic binding of hemoglobin. You know, you guys remember that? I won't get into it too much because it's not really an enzyme. But if you're watching this at home before your exam, you guys should know that you should know what I mean by that. The cooperative binding of oxygen on hemoglobin, right? And how it kind of changes the affinity and the way the hemoglobin molecule works. You know, just as a little side note. You know, but if you don't really know what I'm talking about, it's a good time to go back and rewatch. And then we have heterotropic. Heterotropic, you know, homo, same, hetero, different. In this case, we're going to have the regulation in which the modulator is a molecule other than the substrate. So in this case, we'd see something like substrate B. This would be substrate B coming into the allosteric site. This is still the active site, and substrate A is still filling the active site, but with heterotropic modulation, we're going to have substrate B come into the allosteric site, and that is going to have that enzymatic activity effect, right? But in both cases, and this is where allosteric enzymes differ from our reversible and irreversible inhibitors, in both cases, the activator is not competing for the active site of the enzyme. The active site is full. That's done. That's already filled. Here, they're looking to fill an allosteric site. When we talked about competitive, uncompetitive, mixed inhibition, we're talking about, you know, there's a fight in many cases for them to get to this part of the active site. There's a fight to displace that original substrate. This is totally different from that. Does that make sense, guys? Yes. Good. Okay. So homoheterotropic modulators bind to the allosteric. The only difference is whether the substrate is the same as the modulator molecule or different. Easy enough. All right. Another way these allosteric enzymes differ from the other regulators we talked about, namely the reversible and irreversible inhibitors, is going to be your kinetic properties. Right. So the kinetic properties of allosteric enzymes diverge or are separate from the Michaelis-Menten behavior, at least in terms of kinetics. Okay, so the plots of initial velocity versus substrate concentration, even though we're using the same plot, the actual curve is going to be different. In allosteric enzyme kinetics, that curve, let me draw this. That curve is going to be more of a sigmoid saturation curve, right? It's going to look more like this. In Michaelis-Menten, remember, it looked a little bit more like this. So if you see a sigmoid, if you're looking at this sigmoid curve, you're probably looking at an allosteric enzyme and not a Michaelis-Menten inhibitor, right? They're different. And while they are similar, there's different nomenclature, right? So we have K 0.5 as opposed to Km. So we're going to use, if you see someone, if she gives you on an exam a value and it's denoted K0.5, you're looking at an allosteric enzyme. Okay, not Michaelis-Menten, which would be Km. They're the same idea, but the nomenclature will help you distinguish between allosteric and Michaelis-Menten. That's what that slide is trying to tell you. What's this? Okay, the sigmoid curve. Yes, this is what we just talked about. It all might look pretty familiar to you from the hemoglobin lecture, but remember the R state. We had the R state and we had the T state, the relaxed and the tense state. Well, believe it or not, yeah, these designations are, in terms of allosteric enzymology, these were derived from the work done on hemoglobin. So yeah, it's this nomenclature and these thoughts were based on the hemoglobin lectures. So, the more you know about that, it'll help you understand what's going on here. And yeah, of course, it's important. You have to be able to distinguish between oxygen dissociation curves in hemoglobin and myoglobin and allosteric enzymes. Yeah, they're totally different. But these T and R states, when referring to enzyme kinetics at least, are indeed derivative of the principles discussed in hemoglobin and myoglobin. So, all these lectures are going to tie into one another. So when we look at these curves, what do they tell us? That allosteric enzyme curve, which is going to be our black line over here, that's going to be this line over here. We're actually looking at a hybrid of these two. This black line, this one in the middle, is really, it's like if you took these two lines over here, added them together and took the average, that would be this sigmoidal curve in the middle. Does that make sense? Good. So what makes something more or less active? Well, are more allosteric sites being occupied? The more allosteric modulators that are bound to an enzyme, the more active the enzyme will be. Remember how we talked about how a kind of an allosteric modulator can supercharge the enzyme? Well, you can put a few of them. If you have more allosteric modulators bound to those enzymes, more of the enzyme substrate complexes have that allosteric modulator, then it'll be more active. And we're talking about homotropic enzymes in this slide, right? So based on that knowledge, we know, since these are homotropic, the enzymatic activator and the substrate are going to be the same thing. The allosteric activator is going to be the same thing as the substrate. So we're going to have a substrate in the active site and a substrate in the allosteric site. That's homotropic. Now, if the substrate in the active site was there, but not in the allosteric site, and we had something different in there, that would be our heterotropic. But we're talking homotropic right now. So enzyme, substrate, we'll say this is the allosteric site over here. There's nothing in here. If there's nothing in here, it's inactive. If there is something in here, notice these are both the same, it'll be active. That's your allosteric regulation. That's really all this slide's trying to tell you. All right. Let's talk about the heterotropic modulators. There are a couple of them as well, which is again why I said those charts are going to come in handy. You break these things up into smaller pieces. It's going to really help. Running low, a little bit low on time here. Okay, you know what? Let's just proceed forward. So if something is in the active site and the allosteric site, modulation could still happen. Well, yeah, that's what modulation is. If you have something in the active site and in the allosteric site, then yeah, that is modulation. That's allosteric modulation. Absolutely, yeah. Yes. All right, let me run through this as quickly as I can, but this is also an important slide, so I do gotta cover it, guys. And again, like I said, I have the practice questions ready to go, but I will add them on the slides and post them on Canvas for you to go through at your own time. I wanted to kind of time you guys and make it a little bit of an activity, but it doesn't look like we're gonna have much time for that. Unfortunately, I do apologize. But this content really is important. I have to go through it. So we'll leave the questions for you to use at your own time, at your own pace, after you've looked through all of the material and gotten a grasp. Is that all right? No problem, AM, man. We've all been there. Listen, like I said, if you are 100% confident right now, like, wow, you are the outlier. Okay, most of us are going to have to go back and review this over and over again, and you're going to have to listen to different explanations. Don't feel bad, don't be discouraged. Okay, because the more it hurts to study and the more you're getting things wrong and you're screwing up, the more it sticks. And that's an actual proven study that we went through. All right, you guys, so bear with me, we're almost there. We only have a few more slides left. Okay, let's talk about the two types of heterotropic modulators. Okay, heterotropic. Now we know what we're talking about. We're talking about heterotropic modulators. Now we have one here and something else in the allosteric site. This is our active site. This is our allosteric site. Okay. There's modulation in which the K.5, the K sub 1/2, right? But not the Vmax is altered. Okay. For heterotropic allosteric enzymes, the activators may cause the curve to become more hyperbolic. So a positive modulator, this is a positive here. This is a positive modulator, will cause a shift to the left. A shift to the left. We don't really see these shifts in inhibition, in reversible and irreversible inhibition. If we're talking about allosteric modulation, though, yeah, you're going to see these shifts. And of course, you're going to see them in oxygen, hemoglobin, dissociation curves. But in terms of this, in terms of enzymes, this is where the shifts really come into play. So an activator, right? Because modulation can be an activator or it can be an inhibitor. Again, I'll say that again. Modulation can be an activator or it can be an inhibitor. So activators may cause the curve to become more hyperbolic. So a positive modulator will show a shift to the left. Notice these curves are more hyperbolic. There's much less, there's not really a sigmoid type of look. Here's the sigmoid that we're looking at. You see how it kind of looks like an S over here, a sigmoid? You don't see the S over here. You see it a little bit over here. But as you get more positive, as you have more positive regulation or positive activation, I should say, positive activators, the more you have positive activators, the more aggressive they are, I should say, the more of a hyperbolic curve you're going to see. Okay. And this is for heterotropic allosteric enzymes. Okay. That's important. Okay. What about inhibitors? Here we have inhibitors. Inhibitors will cause the curve to become more sigmoidal. So we're going to basically be seeing a shift to the right. That's going to give us these. That's going to give us these. I mean, this is more linear than anything, but you get the point. Shift to the right is negative. And shift to the left is positive activators. Okay. As we shift to the right, the K sub 0.5, right, or AKA KM, decreases. Just look at these different hash marks here, right? So here, let's look at the Vmax here. Vmax will take 1/2 of Vmax. It's kind of hard when you don't have numbers. You know what? I have a better slide coming up. We'll go over that in a little bit. But just get those two down, okay? Right shift is going to be a decrease in K.5. Left shift will be an increase in K.5. Got just a few more slides to get through, guys. And here's the second category. This was the first category where Vmax is altered, or Vmax is not altered and K.5 is altered. Okay. And here, Vmax is altered and K.5 is not altered. This is much less likely, guys. This is very unlikely to happen in real life, but we are going to go over it. It's modulation in which the Vmax, like we said, is altered, but not Km, the opposite of the first category. Okay, what we just talked about. And what I really need you guys to just focus on is really the graphs. Okay, the graphs are the key, the changes in Vmax and K.5. If you're able to separate Michaelis-Menten enzymes from allosteric enzymes, like you're not going to see a Michaelis-Menten enzyme look like that, really. That's step one. And then if you can distinguish between allosteric, homotropic, and heterotropic regulators on that basis, that's step two. You know, if you become comfortable with that, then you're golden. But you see how this says K.5 and not Km? That's your first indication that this is allosteric regulator. If it said Km, then we're looking at a Michaelis-Menten inhibitor, right? That type of graph. So just take these little clues and these little hints and try to put them all into a little T-chart, and you'll figure it. You'll figure it all out after you look over it a little bit. Okay, before we go forward. No. Okay, this is what we just went over. We did this. Let's talk about covalent modification and then these two, and we're done. So some enzymes are regulated by reversible covalent modification. Here's that little schematic that you were given. You can look at it on your own time, just familiarize yourself with the different types. You know, you got phosphorylation, adenylation, acetylation, myristylation, ubiquitination, which is really important. Who knows what ubiquitination is responsible for? What's that gonna drive in terms of cell processes? ATP, not quite. So ubiquitination is going to target a cell. It's going to kind of, you know, put a few red flags in the cell saying, hey, come destroy us. It's going to target the cell for proteasomal degradation. It's just a way for the cell to tell the rest of the body that, and the proteasomes, hey, we're ready to be destroyed. We're ready to die or be recycled. So, you know, here we are. You can see the ubiquitination on us. Come get us. You know, that's just the body's way of talking to itself, saying and targeting itself for destruction. P53 thing, right? P53 is a little bit different. I don't want to say that they're the same thing. I'm sure they're a little bit involved. You see P53 a lot in cancer biology, and ubiquitination happens in all kinds of metabolic processes and biochemistry. So no, I'm sure they're related in plenty of ways, but you know, definitely not directly related. Something definitely ask Dr. Peterson. She would know much better than I would. Okay, that's that. This, you don't need to know any of this. You got to know that protein kinases will catalyze the attachment of a phosphoryl group to certain amino acid residues. These are them. Don't got to know exactly what they are. Just know that a kinase phosphorylates, phosphatase desphosphorylates. Easy enough. Yeah. Okay. Yeah, you guys are going to become intimately familiar with both of these processes as the semester goes on. You know, it's going to be super, super, super important to know about phosphorylation and dephosphorylation and phosphatases and when they're used and under what hormonal systems. It'll all come into play. But for now, just know a kinase phosphorylates and a phosphatase dephosphorylates. Here is just an example of what we just talked about. Dr. Peterson's explanation is more than enough. No need to reiterate here. This basically just showing the mechanism of how muscle glycogen storage and recruitment is regulated by phosphorylation, like we just said, and how that phosphorylation is regulated by hormonal factors like insulin and glucagon. And you'll get into that a lot more next semester. You will have to know exactly, you know, what is being phosphorylated, what's being dephosphorylated, when, and what that causes. You know, it gets a little bit tricky there too, but again, it's a matter of just really memorizing and going through the process. For now, this is just an example. This is just showing how adding a phosphoryl group using phosphorylase can cause a conformational change. Again, Dr. Peterson added this just to highlight the importance of covalent modification in major processes like glycogenolysis and glycogenesis. You know, these are obviously important things in our day-to-day lives, being able to use and store glycogen for to either break down for energy or turn energy into that storage product. Super important, something we use all the time and every day, and it's ultimately the result of phosphorylation. Okay, we're just going through the importance of it. Okay, some enzymes and other proteins are regulated by proteolytic cleavage, which we talked about already in depth. I'm not going to go more into it, but inactive precursor gets cleaved, becomes active. Same thing with proteins or proenzymes. They're precursors that you cleave with proteolytic cleavage and they become active. That's all you got to know. Okay, so here are some of the practice questions that we're going to go through. We're exactly at 3 o'clock, so I can't go over too much now. I'm gonna just run through what I got laid out for you guys for now. Okay. These are your textbook questions that were assigned to you. Okay, I'm not sure if you went over them in class. I don't think you did because I watched all the enzyme lectures. But here you go. These are the questions. Think about them first before you go to the next slide. And then I gave you the answers and I gave you the explanations for the answers. Okay, so you can take your own time going through these. Okay, calculate the substrate concentration when the enzyme operates at 1/4 max rate, or calculate the Vmax, determine the substrate concentration under these conditions. And that's going to take a lot of thought and trial and error and mistakes. And then I'm going to give you the answers here, but do yourself a favor. Don't just look at the question and then the answer. You know, look at the question and then try to figure it out. If you cannot figure out something on here, if you can't understand how I got to this answer, email me. Email me and I will write it out personally and send it to you, exactly what steps you got to take. Okay. In fact, you know what? I might just do that. I might just go ahead and add all my work directly to these slides, just so you guys have something to, you don't have to email me. It's right there for you. Okay. Curves. We're going to look at a lot of curves. We're going to discuss why enzymes are corresponding to the other. Questions, more calculations. I'll put my work in here. I'll put all my work in here so you guys have it, so you guys know exactly what I did, right? So I have a little bit of a written explanation, but I'll put the actual math in there as well. It might take me until tonight to get everything posted because I do have class, but I'll get you guys that information. Here, a few multiple choice questions. The answers, you know, the answer, and I'll put the slide corresponding to why that's the answer. What can be said about this reaction, right? You go through. These are just some here. Here's that chart I was telling you about, right? I told you guys to make this chart. I did it for you. Here. There's the chart I was talking about, and that should give you a very clear understanding, okay, of what you're looking at. When you get a chart, when you get a graph, or you get figures and numbers and all that, this should help you tremendously. And you guys have that at your disposal now. What could alpha equal alpha prime? in these cases. We know non-competitive goes under mixed, right? And I apologize if I didn't really delve deep enough into certain concepts, and if I didn't and you really are confused, and please do email me and I'll answer you, and I'll try to include some of the answers that I get from you guys to be available to the class publicly without naming names, of course. And that's enzymes, guys. You know, it seems daunting, but it's not that bad, and you can do it. If I did it, believe me, you can do it. I promise you. I am here for you. I am here to help. So is David. I'll try to put up that Star Wars analogy I had for my fellow nerds. And if you guys haven't seen Star Wars yet, then you know what to do after our exam. All right. Okay, guys, listen, I really appreciate you for showing up. Thank you. Thank you so much. Please reach out. I'm here for you. Let's get it. Let's get it. All right. I'll talk to you soon. Much love. Woo, I love it. Okay.
Appreciate you, Steven. Thank you.
I appreciate you, man. Absolutely. Anytime. Reach out whenever. All right.